All right. All right, section 4.1 here. All right, by the time we get done, we will determine what a sample space is and how to construct a sample space. We'll find the probability of an event using classical or probability or the empirical probability method, sometimes called a relative frequency method. Okay. All right. First of all, the probability of an event is the chance of the event occurring. Why do we even need probability? You know, I mean, we got a lot of scientific knowledge nowadays to the point whereby we almost have a formula to explain the occurrence of just about everything. But, ladies and gentlemen, you got to understand that there are some processes or some things that mathematics or science basically just cannot explain. Not to the point whereby we can devise a mathematical model to explain the outcome in a consistent manner every time. There are a lot of things in nature which we don't understand well enough, and therefore we're not able to model the phenomena accurately enough using a definitive mathematical model. In such a situation, oftentimes we have to speak in terms of chance or the probability of something occurring. Okay. For instance, if we have like 150 people playing bingo, we don't have a mathematical model that can predict with 100% accuracy exactly who is going to win during that bingo session. As a result, we have to speak in terms of what is the probability of an individual winning a particular bingo game. Okay, so probability kind of like picks up where exactness leaves off, if you will. All right. So probability is the chance of a particular event occurring. A probability experiment is the process involving chance that leads to well-defined results called outcomes. And experiments in probabilistic circles are a little bit different than experiments that you may have experienced like in a chemistry class or maybe in a physics class or physical science class. These experiments are a little bit different. An example of an experiment in probability would be like maybe flipping a coin or drawing a card from an urn or a box or a container, or randomly selecting an element from a particular container consisting of many elements, right? All right, when you conduct an experiment, whatever the experiment is, there has to be some sort of an outcome. And the outcome has to be well defined. It cannot be like a gray area. But an outcome always is the result of conducting a single trial of a particular experiment. Right? For example, when you flip a coin, all right, there's going to be an outcome. And the outcome is either going to be a head or a tail. Now, the door is left ajar for the possibility that when you flip a coin on like a table or a surface, the coin could land on edge. But the probability of that occurring is very small. And I can guarantee you that if you flipped a coin 100 times, it probably would not land on edge any one of those times. Okay. It would either definitively land on either a head or a tail. All right. But, what's interesting is that the door is left open a little bit for the possibility that a flipped coin could land on edge. All right. All right. Now, when we conduct a probability experiment, we always have what's called a sample space. And this sample space basically clearly lists all the possible outcomes of the particular experiment. For instance, when we flip a coin, our sample space would be a set consisting of all the outcomes, which would be head or tails. All right. So like if I flip a coin, we would denote the sample space as being S is equal to head or tail. That would be the sample space of flipping a coin. Okay. If you roll a die, all right, die is singular, which means one six-sided cube. The sample space of rolling a die would be the set consisting of the numbers 1, 2, 3, 4, 5, or 6. That would be the sample space of rolling a die. All right. Okay, so sample spaces are always sets consisting of all the outcomes of a particular experiment. Now, if we roll two die, we roll two dice, therefore, and keep track of the results of each roll. The sample space consists of every possible combination of value for the first die and the value for the second die is shown on this chart. And I don't know, maybe we can blow this chart up here so we can see it. We have a column that consists of die one's results, and we have a row that consists of die two's results here. So die one could yield a 1, a 2, 3, 4, 5, or 6, and likewise for die two. So how many possible outcomes are there when you roll two dice? Well, there is 6 times 6, or 36 possible outcomes. For instance, you could roll a 1 on die 1 and a 1 on die 2, or you could roll a 1 on die 1 and a 2 on die 2, or a 1 on die 1 and a 3 on die 2, a 1 on die 1, a 4 on die 2, etc., 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 etc. Okay, so there's 36 possible outcomes when you roll two dice. All right, or and you have the dice labeled as die 1 versus die 2, or this would also be the result if you roll one die 2 times. Okay, there would be 36 possible outcomes. All right, that makes sense there. All right, tree diagrams are very useful in helping us to enumerate all the possible outcomes of various probabilistic experiments. Suppose that a family, to illustrate that, suppose we have a family that has 3 children. What is the sample space for the genders of the children? Well, this tree diagram down here can help us out. The first child could be a boy or a girl, so we make 2 branches from a starting point, 1 for each possibility. The second child could be a boy or a girl, so we make 2 branches from the end of each branch of the previous step. And we continue to repeat this process as long as we continue to have children, okay? So if you look at the first child, notice you have 2 main branches emanating from a point to the left here. This is kind of like the root of the tree. We could have a boy or we could have a girl. That's for the first child right here. All right, the second child, notice we could have a boy or a girl from the first particular gender. And then the third child, we could have a boy or a girl from the previous second child. Okay. And if you follow the branches of this tree, you can enumerate all the possible outcomes of a couple having 3 children. So in other words, you could have a boy, or you could enumerate as a boy, or a boy, boy. That's one outcome. Or you could have a boy, and a girl, boy, boy, girl. Or you could have a boy, a girl, and a boy, boy, girl, boy. Or you could have boy, 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 girl, excuse me, and then a girl, boy, girl, girl. Or you could have girl, boy, boy, or girl, boy, girl. Or you could have a boy, girl, excuse me, or you could have, excuse me, a girl, and a boy. Or you could have a girl, and a girl. All right, so there are, notice 8 possible outcomes here. Another way of determining how many possible outcomes or arrangements you could have is you could think of having like 3 empty mailboxes, one for the first child, one for the second child, and one for the third child. All right, how many genders could occupy the first mailbox? There's 2. How many genders could occupy the second mailbox? Again, there's 2. And how many genders could occupy the third mailbox? There's 2 possibilities. Well, if there's 2 ways to have the first child occur and 2 ways for the second child to occur and the 2 ways to have the third child occur, then by the fundamental principle of counting, there would be 2 times 2 times 2, or 2 to the third power, or 8 possible ways of having 3 children, as far as gender is concerned. That's called the fundamental principle of counting. Okay. Does everybody see that there? Okay. All right. Now, ladies and gentlemen, there is another way we could have computed this 8. We could have realized that this is called a permutation, in the sense that order does matter, in which we do have these children as far as gender is concerned. In other words, having a boy first, a boy second, and a girl third is considered to be a different outcome than if we have a boy first, a girl second, and a boy third. All right. So if order matters, we have a permutation. And we're going to try to have 3 children. And there's 2 possible arrangements for each child. This is called a permutation. Okay. Now, the permutation formula, n permuted r ways, is going to be equal to n factorial divided by n minus r factorial. Now, what's this factorial function in mathematics? Well, the way it works is this way. N factorial is defined to be equal to n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times dot, dot, dot. This goes on down the line all the way till we get down to 2 times 1. Okay, it's called a permutation. So if you look at 5 factorial, if you will. This is called a factorial. I'm sorry, I called it a permutation. 5 factorial. 5 factorial would be 5 times 5 minus 1 or 4 times 5 minus 2 or 3 times 5 minus 4 or 5 minus 1, 5 minus 2, 5 minus 3, which is 2, or 5 minus 4, which is 1. So 5 factorial is 5 times 4, which is 20, times 3 is 60, times 2 is 120, times 1 is 120. That's called 5 factorial. So that's how the factorial function works here. So if we are going to have 3 children, where order matters as far as the gender is concerned, and there's 2 possible genders per trial, if you will, that should give us 3 factorial divided by let's see. 3 factorial divided by 2 is 2. Okay. We'll get rid of that there. Okay. So this is a permutation here, and now this permutation is used to enumerate possible outcomes where order does matter. But as far as doing our gender outcomes here, there would be 8 possible outcomes here according to the fundamental principle of counting. So the permutation is not really going to help us with this situation, but the fundamental principle of counting does guarantee we're going to have 8 outcomes here. All right. Now, as far as like enumerating all the possible outcomes, you could see where this would become very, very cumbersome. For instance, if we had 10 children, ladies and gentlemen, this tree would get larger and larger and larger as we go to the right. And this would become very impractical, if you will, because 2 raised to the 10th power would give us a very, very large number. All right. So normally, when we compute probabilities, we're going to keep the problem somewhat manageable, whereby we can actually list all the possible outcomes. Okay. And we won't have to, deal with something that's out of control. In reality, when you're dealing with computing the probability of having a different gender during a different trial or a birth, this is ideally suited for a discrete probability distribution called the binomial probability distribution. Because every trial is a Bernoulli trial in the sense that when you have a child, there's going to be 2 possible outcomes, either a boy or a girl. There's no other possible outcome. All right. And so, ladies and gentlemen, whenever you have a Bernoulli trial for any experiment, that experiment can be modeled according to the binomial probability distribution. And we'll look at that a little bit later on. But now we're just keeping this kind of simple where we only have 3 children. Okay. And we can actually enumerate all the outcomes here. So all of these outcomes would be found in the sample space for this experiment here. All right. Okay. Wait a minute, what just happened here? Hold on a second here. Hold on a second. I lost my cursor or something here. What's going on? What the? All right, I don't. All right. All right. An outcome of a probability experiment is an outcome of a single trial of the experiment. For instance, if I flip a coin just once, okay, the outcome, whether it's a head or a tail, would be considered to be an outcome. All right. Now, an event, however, ladies and gentlemen, is 2 or more outcomes of a probability experiment. So, for instance, if I'm rolling a die, let's say, what would be the probability of rolling like an even face? Okay, we could define that to be an event because there's more than one possible outcome there. Okay, we could roll a 2, 4, or a 6. All right. All right, so we can have simple events in which there is only one possible outcome defined to be the event, or we can have a compound event where there's more than one outcome, okay, for a particular event to occur. And that would be like rolling an odd or an even face on a die. Or that would be like a a probability of selecting a jack from a standard deck of cards, something like that. All right, there's two main ways for computing probabilities that we're going to explore in this section. And the first way is called the classical probability way. Sometimes this is also referred to as the equal likelihood model for computing probabilities, in the sense that every element in the sample space of the experiment has an equal chance of being selected on any given trial of the experiment. That's the key assumption. We would call this an equal likelihood model, okay? Or it's sometimes coined as being a classical probability way of computing these chances or probabilities. All right. For instance, if we have a fair coin, and what does it mean for our coin to be fair? Anybody? What does it mean to say we have a fair coin? If we have a fair coin,
does that mean it was like it landed on the side?
well, a fair coin means that there's no bias in the coin. It's not weighted on one side or another, okay, disproportionately. So a fair coin means that when we flip the coin, there's an equal chance of either getting a head or a tail. Now, if the coin is weighted in any way, shape, or form, then the probability of getting a head or a tail in any given flip may not be 50-50 or may not be equal in chance. That's called a weighted or unfair coin, okay? When you go to the casino and you start playing those games, card games and dice games, we're assuming that the cards and the dice are fair. They're not weighted in any way, okay? So if we have a fair die, then the probability or the chance of rolling a 1, 2, 3, 4, 5, or 6 should all be equal, all right? There should not be any bias favoring one face over another if the die is fair, all right? All right, so assuming that we have a fair sample space, if you will, where every element in the sample space has an equal chance of being selected or turning up on a trial of an experiment, then, ladies and gentlemen, the probability of some event E occurring, however we define event E to be for whatever experiment we're conducting, is computed by taking the number of ways that event E can occur and dividing it by the total number of possible outcomes for the particular experiment on any given trial, okay? This is called the equal likelihood way of computing a probability. By taking the ratio of these two counts or numbers, we compute the probability of event E occurring. Right. Now, the probabilities that we're going to work with in this class can be expressed either as reduced fractions or as decimals, rounded to 3 places. So they want these decimals to be rounded to the thousandths place. If the probability is extremely small, however, then you can opt to round to the first non-zero digit after the decimal point. So some probabilities are so small that sometimes you have to go beyond 3 decimal places to round it. Bottom line is this: whenever you compute a probability of an event, probabilities are always going to be a decimal or a fraction between 1 and 0. You're never going to compute the probability of an event and it being like 2 or being like -4 or something like that. Probabilities are always between 0 and 1 inclusive, right? Whether they're decimals or fractions. So that's important to understand. So like, you know, we're used to hearing like, well, the probability of rain tomorrow is like 30%. Well, yeah, 30%, but we don't express probabilities as percents in here, ladies and gentlemen. We would express 30% as 0.30 or 0.3. That's how we're going to express probabilities. In our minds, we know that to be 30%, but we don't express it that way in this class. We express them as decimals or fractions between 0 and 1. All right, if you go back to our gender example where there's 8 possible outcomes for having 3 children, assuming that each gender has an equal chance of occurring on any given trial or birth, that's the key assumption, then we can use the equal likelihood model for computing probabilities. So in the classical or the equal likelihood probability point of view, each outcome is equally likely. So the probability of each outcome, okay, is going to be 1/8 or 0.125. Okay, so the event, suppose we define event, some event E to be that we have exactly 2 girls when we have 3 children. Okay, well, how many ways can that event occur? How many ways of the 8 can we have exactly 2 children? Excuse me, 2 girls. Well, if you go back to the tree here, how many of the 8 ways yield exactly 2 girls? It's not going to be this one, not this one, not this one, this one. There's 2 girls. Not this one, there's 2 girls, and here's 2 girls. So 3 out of the 8 outcomes yield exactly 2 girls. And therefore, the probability when we have 3 children of having exactly 2 girls, according to this equal likelihood model way of computing probabilities, is going to be 3 divided by 8, which is 0.375. In our minds, we know that to be about almost about a 38% chance that we're going to have exactly 2 girls when we have 3 children. Okay. All right, the probability of an event, any event E occurring, again, must be a decimal or a fraction between 0 and 1. And if the probability of some event E occurring is 0.5, we would say there's a 50-50 chance of that event occurring. Any probability that's less than 50% or 0.5 is deemed to be more unlikely to occur. And any probability greater than 0.5 is deemed to be more likely to occur. The probability of if the probability of any event E occurring is 0, we would say that the event is impossible to occur. If the probability of an event is equal to 1, then we would say that there is 100% certainty that that event will occur. Okay. Now, this is critical. The sum of all the probabilities of all the outcomes in a sample space for any probability experiment must always add up to 1. For instance, when we roll a fair die, the outcomes could be 1, 2, 3, 4, 5, or 6, assuming, because it's a fair die, that each outcome has an equal chance of occurring. The probability of rolling any one of these faces would be 1/6. Notice if you add these probabilities all together, 1/6 added to itself 6 times, you do get exactly 1, right? So that's critical. Whenever you have a probability experiment and you have the sample space with all the outcomes of the experiment, the sum of all the probabilities from that sample space must always be equal to 1. And that becomes more important when we start getting into probability distributions, whether discrete or continuous down the road. All right, what is a complement of an event E? Well, a complement of an event E is the set of outcomes in the sample space that are not in the event E. Symbolically, in this textbook, your author is going to represent the complement of an event as the name of the event in uppercase letters with a bar over it. So E bar is read as the complement of event E. All right. Now, you could also think of the complement event E as being the event that E does not occur. For example, the complement of rolling an even number on a fair die would be rolling what? An odd number on a fair die. Those are called complementary events. All right. And the event and its complement make up the entire sample space. So they have to be collectively exhaustive. They have to exhaust all possible outcomes in the sample space. So the sum of the probability of an event and its complement is always equal to 1. And that's represented by this very important rule here. The probability of some event E occurring plus the probability of the complementary event to event E occurring is always equal to 1. Right? In other words, if I define event E to be that that a light bulb is off, then what would be the complementary event?
The light bulb's on.
Light bulb is on, correct? All right. If event E is the event that a computer, let's say logic gate is in a high voltage state, what would be the complementary event to that event? Well, the complementary event to the event that a computer logic gate is in a high voltage state would be to say that it's in a low voltage state. Okay. All right. Notice we can do algebra on this equation and we can solve it for any one of these probabilities just by subtracting the other one from both sides. So these are two equivalent alternative versions of that very important fact that relates the probabilities of an event and its complement. A Venn diagram, ladies and gentlemen, from set theory helps us to visualize the relationship between an event and its complement, if you will, and also the probabilities thereof. If you look at this picture to the left here, suppose the probability of event E occurring is represented by the area of this circle, which is in white here. Okay, and notice the probability of our sample space is equal to 1. So the probability of event E occurring is a subset, if you will, of the probability of the sample space occurring. All right. So what would be the probability of the complementary event E bar occurring? Well, that's going to be 1 minus the probability of event E occurring, which means that it's going to be equal to this white shaded area outside of the blue circle. Okay, so you can think of events as being also like sets, and you can relate events to set theory as far as unions and intersections are concerned, like you talk about in set theory. Okay. Okay. All right. Suppose we return again to the example of a family with 3 children. The event, suppose we define event E to be that at least one of the children is a girl. To say at least one of the child is a girl is to say what? That we could have exactly 1 girl, or we could have what? 2 girls, or we could have what? All 3 girls. That's what at least 1 means. It means 1, 2, or 3. And so, ladies and gentlemen, how many of the 8 outcomes yield 1 girl, or 2 girls, or 3 girls? Well, if you go back and count all the outcomes that yield 1 girl, 2 girls, or 3 girls, this one doesn't count. There's 1 girl, 2 girls, 1 girl, 2 girls, 2 girls, and 3 girls. So it looks like 7 out of the 8 outcomes are ways of having this event occur, of having at least 1 girl. So in other words, the probability of having at least 1 girl when we have 3 children would be 7/8 or 0.875. In our minds, we know that to be about 87% or 88% chance of that occurring, correct? All right. Now, that was the difficult way of computing that probability. Is there an easier way? And the answer is yes. The easier way is to make use of the complementary probability rule we just seen. So the probability of having at least one girl could have been computed a little bit more efficiently by saying that it's equal to 1 minus the probability of not having at least one girl. Well, what does it mean to say not have at least one girl? Well, that would mean that we have no girls. We have all boys. Well, all boys only occur 1 out of 8 possible ways. So therefore, the probability of having at least one girl is equal to 1 minus the probability of having no girls. 1 minus 1/8 or 1 minus 0.125, 0.875. So this complementary probability rule can speed things up big time when computing probabilities of various events. All right, you see, to compute the probability of having at least one girl, the long way, we had to go back and count all the ways that could yield one girl or exactly 2 girls or 3 girls. That took longer than if we just said 1 minus the probability of having no girls, or in other words, 1 minus the probability of having all boys, because there's only 1 out of 8 ways of having all boys. Subtract that from 1, and you get the probability of having at least one girl. Do we understand this complementary probability rule and how it helped us there? We'll be using that more in the future. All right, there's another way to compute probabilities. It's called the empirical rule method, or sometimes we call it the relative frequency way of computing probabilities. And for this particular model, ladies and gentlemen, we do not assume and cannot assume that every outcome in a sample space for a probability experiment has an equal chance of occurring. So if you don't have an equal likelihood model, then you really should be using this empirical probability rule or this relative frequency probability rule to compute probabilities, as opposed to the classical method, which requires that you have equal chances for any outcome to occur. All right. For example, instead of assuming a coin is equally likely to come up heads or tails, suppose the coin is weighted in some way, shape, or form. All right. Well, if we know the coin is, like, let's say, unfair or biased or weighted in any way, then in order to determine various probabilities for flipping that coin, we may want to, kind of like see how unbiased it is by maybe flipping the coin 1,000 times and seeing how many of the 1,000 trials yielded heads. Okay. Suppose that 543 of the tosses came up heads and 457 of the tosses came up tails. Then what we're going to do is we're going to divide the frequency of each outcome by the sum of the frequencies of all the outcomes to determine its probability. So the probability of an event surrounding this particular weight, which appears to be an unfair coin, of event probability of event E occurring is going to be equal to frequency of the number of times event E does occur in n total trials of maybe flipping that coin. Okay. So the probability of a heads for this particular situation here with our coin, which may be unfair or biased, would be 543 out of 1,000, or 0.543. And the probability of the complementary event of flipping a tail would be 1 minus 0.543, or 457 divided by 1,000, 0.457. Okay. Let me give you another example of this empirical probability rule. Now, ladies and gentlemen, suppose that I was to go to a basketball hoop and stand a certain distance away from it and take 10 shots at the basketball hoop. And suppose that in 10 shots I made, let's say I made 6 out of the 10 baskets. Okay, that means I made 6 out of the 10, but I did not make 4 out of the 10. What do you think then would be the probability of making the 11th shot would be? Well, based on what I told you, the past relative frequency of occurrence of making a basket, you would use this empirical probability rule, because trust you me, when I take a shot at a basket, ladies and gentlemen, there is not an equal chance that I will make the shot or miss the shot. Believe you me, with my situation, it is weighted more favorably that I probably will not make the shot as opposed to making the shot. Okay. And for somebody else, it might be weighted the other way. So this is not an equal likelihood or fair situation here when I shoot the basket at the hoop. Therefore, to compute the probability of making the 11th shot, I would have to base that off of what has occurred in the past with my basket shooting. And therefore, I would say the probability of making the 11th shot would be about 6 out of 10 or 60% chance. Make sense? This is the empirical probability model, or the relative frequency way of computing probabilities when outcomes are not all equally likely to occur. So again, it just depends what kind of situation you got. If you have a fair situation where all outcomes are equally likely to occur, then you want to use the classical way of computing the probabilities and not this way. But if you don't have an equal likelihood situation, you better be using this empirical way. Now, there is a law in probability called the law of large numbers, which basically says this, ladies and gentlemen: if you keep repeating an experiment many times, all right, then relative frequencies ultimately approach true probabilities. Okay. So what I'm trying to say, ladies and gentlemen, I can portray in symbols here. So as the number of trials of an experiment approaches infinity, in other words, as we conduct more and more trials of an experiment, maybe like flipping a coin, then the probability of the relative frequency of occurrence of some event E, which is computed by taking the number of times event E occurs, depending upon the number of trials. In my denominator here, I should have the number of trials here. Okay. I should just have the number of trials. Well, what happens is this relative frequency, okay, the number of times that event E occurs divided by the total number of trials. What happens to this relative frequency here is it actually approaches the true probability of the event occurring. That's what the law of large numbers guarantees. Okay, so relative frequencies of occurrence of event actually approach the true probability of that event occurring as the number of trials approaches infinity, or a very large number of trials of an experiment. So the bottom line is this: if you know your coin is like unweighted, or excuse me, is weighted or unfair or biased, then to compute the probability of like tossing a head or a tail can only be determined if you toss that coin many times. Okay, because then your relative frequency of occurrence of tossing heads or tails is going to actually approach the true probability of tossing a head or a tail. That's called the law of large numbers. All right. All right, so let's see if we can go have a little bit of fun. In our textbook. All right. Now, we're going to go to our textbook here.
We just found it.
Okay, so we're going to go to section 4.1. All right. Now, another thing, ladies and gentlemen, is we've already seen all the way possible outcomes of rolling 2 dice. We've seen that in the lecture, the PowerPoint lecture. But how about a standard deck of cards? We got to get this straight right here and right now if we're going to ever do any probability involving cards. What is a standard deck of cards? Well, for our purposes, a standard deck of cards, okay, has 52 cards in it. There's going to be 4 different suits: hearts, diamonds, spades, and clubs. There's 13 cards per each suit. So 4 times 13 is 52 cards. There are no jokers in a standard deck of cards for our purposes in this course. Okay. The 13 cards of each suit is going to be an ace, a 2, a 3, 4, 5, 6, 7, 8, 9, 10, or our face cards. Jack, Queen, King are considered to be face cards. They have faces on them. Okay. All right. This is a standard deck of cards that we're going to use in this course whenever we compute probabilities involving cards. All right. So I want to get that straight there. This is an example 4.2 in your textbook if you need to look at this picture, because I got in trouble in the past many times by assuming that we all know what a standard deck of cards is. Most of us maybe do, but there's always somebody out there that they maybe never played cards before and doesn't have a clue what a standard deck of cards is. All right, so that's a standard deck of cards. All right, let's move on. Go down and have a little bit of fun with our problems down here. We have ample time here to do quite a few problems. So. All right, the first one here. What is the definition of a probability experiment? Well, do you think a probability experiment would be equal to like me going into the lab and dissecting a frog? Is that considered a probability experiment? Anybody?
No.
I would say no.
Probably not. Do you think a probability experiment would be me going into a lab and trying to separate oxygen and hydrogen from water? Is that considered
No.
to be a probability experiment? Probably not, correct? All right. Do you think a probability experiment would be me going into a physics lab and trying to determine the acceleration of gravity on planet Earth?
No.
Probably not. Can anybody give me an example of a probability experiment? Anybody, anything? Probability experiment.
Rolling a dice.
Rolling dice or rolling a die or anything else. That's one.
Drawing a card.
Yep, drawing a card. Okay, from a well shuffled deck. Okay, that'd be another example of probability experiment. So those are probability experiments. So there are differences between, experiments that we're maybe used to from some of the science classes we take. All right, does anybody want to define for us what a sample space is? A sample space. What's a sample space associated or affiliated with a probability experiment?
The set of all possible outcomes.
Yeah, it's a set of all possible outcomes of a particular experiment, whatever the experiment is. The experiment could be, just like flipping a coin, and the sample space would be nothing more than heads or tails. Or, drawing a card from a deck of cards. And depending upon what we would be interested in, suppose we were interested in the suit of the card that we draw from the deck of cards. Then the sample space would consist of what if we were concerned about the suit? What would the sample space be in that situation? That would be a set consisting of what? If I was interested in the suit of a card drawn from a deck. Well, it would be the set consisting of all the possible suits that could occur, such as a heart or a diamond or a club or a spade. Okay. All right. Number 3. What is the difference between an outcome and an event? Anybody? Outcome versus event.
Outcome is the result of the single trial of the probability experiment.
But an event can consist of more than one outcome. Okay. For instance, if we roll a die once, all right, the outcome could be like a 1 or a 2 or a 3 or 4 or 5 or 6. Okay, it's just going to be one of those faces. But suppose I define event E to be when I roll a die to be defined to be that I roll like an even face. Well, then that event could occur if I roll a 2, 4, or a 6. So there's more possible ways for an event to occur as opposed to an outcome to occur. All right, what are equally likely events? We say events are equally likely provided what? Equally likely events are events where the
They have the
probability.
same
Go ahead.
They have the same probability of occurring.
That's correct. So we say events are equally likely if they all have an equal chance of occurring, okay, or equal probability of occurring. Okay. Now, what is the range of the possible values of a probability of any event occurring? What's the range of values? In other words, when you compute the probability of any event occurring, it must be either a decimal or a fraction between what and what? Between what or what?
0 and 1.
0 or 1, including 0 or 1. I mean, the probability of some events is actually equal to 0 or actually equal to 1, for certain situations. In other words, I think it's safe to say that if I define event E to be that it rains 2 days in a tropical rainforest, what's the probability of event E occurring over the course of a year? Well, I would probably think that that would be very close, if not exactly equal to what? What do you think? 1 maybe? 100% chance in a tropical rainforest? If an event cannot happen, what value is assigned to the probability?
0.
0. What is the sum of the probabilities of all the outcomes in a sample space always equal to? Always. The sum of the
1.
probabilities, of all the outcomes of a sample space has to always be equal to 1, always. 9, if the probability that it will rain tomorrow is 0.20, what is the probability that it will not rain tomorrow? In other words, if event E is that it rains tomorrow, the complementary event E bar, would be what? That it does not rain tomorrow. So if we define this event to be event E, then the complementary event that it won't rain tomorrow would be E with a bar over it. E bar. So what do you think, Lizanne? What's the probability that it will not rain tomorrow? This is symbolically how we represent this. The probability that it will not rain tomorrow is equal to what? You might remember the complementary probability rule we've seen? It's equal to what? 1 minus the probability of what? Event E occurring? So the probability it will not rain tomorrow is going to be 1 minus 0.2. Or it's going to be 0.80. That's the probability it will not rain tomorrow. 80% chance, okay? That's called a complementary probability rule. And that's a very important rule, especially for various probabilities. It can save you a lot of time. All right, any questions so far here? All right, number 10, a probability experiment is conducted. Which of these cannot be considered to be valid probabilities of an outcome? Could 5/8 be a valid probability of some outcome, ladies and gentlemen?
Yes.
Yes, that's valid. Could 0.29 be a valid probability?
Yes.
That's possible. Could negative 1/3 be a valid probability?
No.
No, probabilities can never be negative. Could 2.14 ever be a valid probability of some event?
No.
Nope, because probabilities are always decimals that lie between 0 and 1. Remember, the probability of any event occurring is always a decimal or fraction between 1 and 0 in this course. Okay. Now, you might think of it as being like 20%, but don't write it as 20%. Okay. We just write it as 0.20 or 0.2. How about E? Is this a valid probability? Negative 63/100ths or negative 63%? That's impossible. Can't have negative probabilities. F, is 0 a valid probability of some event?
Yes.
Certainly possible. 1 is a valid what? Probability. Do you agree? That's possible. Is 153% possible?
No.
Not in this course, it isn't. If it was 153% chance, 153% chance is a decimal is 1.53, but that's not even possible because probabilities cannot exceed 1 or 100%. Not possible. All right. How about 87%? Is that a valid possible probability for an outcome? This is a tricky, slippery little question here, ladies and gentlemen. This could be answered either what? Yes or no. How could I say no?
No in that form.
No, because remember, probabilities strictly are to be what? Decimals or fractions between 0 and what? 1. Do you agree? Yes, because, okay, I know we see 87%, but we wouldn't write it this way. We would write 87% as what decimal? 0.87, which is a valid probability. So I don't know. This one here, kind of a gray area there. Okay. So that could go either way if you interpret it one way or another. All right. Technically, probabilities are decimals and fractions between 0 and 1. So we'd probably say no for this guy if we adhere to this strict definition here. Okay. For probabilities. All right. Let's move on. All right. Classify each statement as an example of having used the classical or the empirical way or a subjective way of computing probabilities. Remember, the classical way is an equal likelihood model where all outcomes are deemed to have an equal chance of occurring. Empirical probability is based on like relative frequencies of occurrence of an event in the past. Subjective probability is just like firing from the hip, I guess. We're not really going to get into subjective probabilities too much, but let's see if we can try to figure this one out. The probability that a person will watch the 6 o'clock evening news is 0.15. Do you think there's an equal likelihood chance of a person watching the news exactly at 6 o'clock every night? No, I don't think so. Life gets in the way. Do you agree? In our schedules? Probably not the classical way of computing the probability. It might be based on the empirical, the relative frequency method, based on, how many times you've watched what? The 6 o'clock news in the past, do you agree? Over the last year. So you could argue that it could be maybe empirically computed. Let's see what they got here. Yeah, they do say empirical. All right. How about the probability of winning at the Chuck a Luck game is 536. Well, do you think the odds, do you think that this is equal likelihood of winning this game? I don't know. I mean, this is debatable. We don't even know anything about this game. I mean, it could be equally likely chances of winning or not winning. We don't know. So I don't know. Some of these have some gray areas in them. Let's see what they said. Classical. They did say equal likelihood. So I guess we're assuming that the chance of winning and losing is equal. So. All right. The probability the bus will be in an accident on a specific run is about 6%. How do you think they figured that out? How do you think they would even figure that out? 6% chance. What would they even base that on?
I mean, maybe sitting and watching them go by on this particular stretch for a year.
Yeah, there you go. So that would definitely be like a what? A relative frequency way then. Do you agree? Of computing this probability? Based on the number of observances, how many buses got into an actual accident. Yeah, that's relative frequency. That's the empirical way of computing the probability. I don't think this is an equal likelihood. We would sincerely like to think it's not. Do you agree? Chance of getting into an accident is 50-50. That's no good. I wouldn't want to be in that vehicle. This is probably what empirical. No, I selected the wrong one. Excuse me. Yeah, it's empirical. The probability of getting a royal flush when 5 cards are selected at random. Well, first of all, do we even know what a royal flush is? I mean, not everybody plays poker, correct? Can anybody remind me what a royal flush is? Because I'm a little shy in that department myself. What's a royal flush? Anybody?
Isn't it having all the face cards?
All the face cards? I don't know. I'm asking. I don't know. I would have to look it up myself because I don't play poker. So I don't know. I've heard of it before. I've seen it once before, but I don't remember it. All right. Well, anyways, the probability of getting a royal flush when 5 cards are selected at random. Notice these cards are selected at random. Is 1 over 649,740. Because these 5 cards are selected at random, that's the key, randomly selected. We're assuming that the deck has been randomized or it's been well shuffled, which means that each card probably has a what? Equal what? Chance of being selected. Do you agree? In that situation, the deck is not weighted or biased in any way. If we go with that, it would be classical, okay? Equal likelihood model way of computing that probability. All right, let's move on here. Okay, number 13A. If a die is rolled 1 time, what's the probability of getting a 9? We will assume it's a fair die. Anybody? What's the probability of rolling a 9 on a fair die? Hold on a second. Sorry about that.
Wouldn't it be
Well,
zero?
yeah, how many ways can a 9 occur?
0.
Out of how many possible outcomes when you roll a die?
6.
6. 0 divided by 6 is what? 0. That'd be the probability of rolling a 9. 0. B, getting a number greater than 2. What's the probability of rolling a number greater than 2? Well, to roll a number greater than 2 means you'd have to roll a 3 or a what? 4 or a 5 or a what? Or a 6. How many ways can this event, which is a compound event, notice, how many ways can this compound event occur? 4 ways. Do you agree? Divided by how many outcomes when you roll a die? 6 outcomes. The probability is 4/6 or 2/3, or as a or a decimal, about what? 0.67, correct? About a 67% chance, 0.67. That would be the probability of rolling a number greater than 2. What's the probability of rolling a number less than 7? What do you think? How many ways can you roll a number less than 7?
6.
6 ways. Divided by 6 possible outcomes. 6 divided by 6 is 1. In other words, there's 100% chance, ladies and gentlemen, when you roll a die, you're gonna roll a number less than 7. I think that's pretty clear, pretty obvious. What's the probability of rolling a prime number on a die? Well, first of all, what's a prime number? Because if we don't know what a prime number is, all bets are off. A prime number, ladies and gentlemen, is a whole number, okay? Not equal, okay, greater than 1, that is divisible only by 1 and itself. So what are some prime numbers? 2 is a prime number, divisible only by 1 and 2. Is 3 prime? 3 is prime, divisible only by 1 and 3. Is 4 prime? 4 is not prime because 4 is divisible by 1 and itself and also 2. 5 is prime. 6 is not prime. 7's prime. 8's not prime. 9's not prime. 10's not prime. 11's prime. 12's not prime. 13's prime. All right, there's an infinite number of prime numbers. What's the probability of rolling a prime number when we roll a die? How many ways can it occur?
Three.
3 ways. So there's 3 ways for a prime number to be rolled on a die, divided by 6 possible outcomes. This reduces down to 1/2. In our minds, we know this as being a 50% chance of rolling a prime number. That's how you would express it, one of these ways. Okay. All right, let's move on. Okay. All right, now for this problem here, ladies and gentlemen, I would have to go back in order to answer these questions here. I would have to go back and first of all, in the section, I would have to go back and I would have to snip this picture here. I gotta snip this picture. Hold on, get my snipping tool. Okay. Minimize this. Let's go back to the problem now. All right, if 2 dice are rolled at one time, find the probability of getting these results, a sum of 9. Well, a sum of 9. Okay, of the 36 outcomes, ladies and gentlemen, how many of them yield a sum of 9? Well, how can we get 9 out of the deal? It's not going to be any of these. 1 plus 1 is 2. 1 plus 6 is 7. 2 plus 6 is 8. It's not going to be any of these. We could roll a 3 and a what? 6. Do you agree? There's one way to roll a sum of a 9. We could roll a what? A 4 and a 5. There's another way to roll a sum of 9. Or we could roll a 5 and a 4. There's another way to roll a sum of 9. Or we could roll a 6 and a 3. So how many ways can we roll a sum of 9? How many ways? 4? Divided by how many outcomes? 4 divided by 36. 1/9 is the probability of rolling a sum of a 9. Okay. Anybody see that there? 4 out of 36 ways. All right. Now, what's the probability? In fact, I want you to do this one for classwork number 1. Classwork 1B. What's the probability of rolling a sum of 4 or 5? Sum of 4 or 5. Let me put this back here. And erase these. All right, ladies and gentlemen, classwork number 1. Compute the probability of rolling a sum of a 4 or a sum of 5. We'll call that classwork number 1. Go ahead and do that. All right, ladies and gentlemen, what'd you get? Anybody get that? Some probability of rolling a sum or a four or five. Out of 36 outcomes, how many ways can that occur?
Seven.
Mm-hmm. We can see there's 7 ways in which you can roll a sum of 4 or a 5. So the probability of rolling a sum of 4 or 5 would be 736. You could roll a 3 or a 1, 2 or 2, 1 or 3, 4 or 1, 3 or 2, 2 or 3, or 1 or 4. Okay. It's making sense here, basic probability so far. All right. Okay, ladies and gentlemen, let's try this one here. Number 17, if one card is drawn from a deck, find the probability of getting these results. We're assuming it's a standard deck of cards, but it's been well randomized, well shuffled. And so we're going to use the equal likelihood way of computing the probability in the sense that any card drawn has an equal chance of being selected. Okay. What's the probability of rolling a 3 or a diamond? Well, hold on. I got to go up here and snip this here.
4 to 1 sample spaces and probability.
What did I just,
ES and complements.
what just happened there?
Sample space and classical probability.
Hold on a second.
57 of 9.
What did I,
4 to 1 sample spaces and
I don't even know what I clicked. Okay, whatever. That's a learning curve for me. Now, let me snip this and bring it to our problem so we got something to look at. All right, let's try this here. All right, let's go back down to our problem. Okay. All right, let's see if we can bring this up. So we got something to look at. It would have to be huge like this. Shrink it a little bit here. We can. Okay. What's the probability of selecting a 3 or a diamond? Well, and how many ways can that event occur? A 3 or a diamond? Well, you could select a 3 4 different ways. Do you agree? Either a 3 of hearts, a 3 of diamonds, 3 of spades, 3 of clubs. Or, ladies and gentlemen, we could select a diamond how many different ways? $13 different ways. We could choose an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Okay. So how many different ways can this possible outcome occur here?
If they overlap like that, do you count them twice or do you just count it one time?
Very good question. We're going to see in 2 days when we look at the addition rules of probability that we cannot double count the 3 of diamonds twice, only once. For this situation, we only count it once. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, what, 16? There's 16 different ways in which what? We could select a 3 or a what, diamond, correct? Okay. So, since there's 16 out of what, 52 ways, the probability would be 16 over 52. And can we reduce 16 over 52? I believe that reduces down by 4, down to what? 4/13. And that would be your probability. 4/13. That's the probability of reaching into a randomized deck and pulling out either a 3 or a diamond. But yes, we have to subtract, we cannot double count the 3 of diamonds. That's very important. All right. All right, how about the next one here? Let's see. All right, ladies, what's the probability of pulling or of selecting a red 6? How many different ways can we select a red 6?
2 out of 52.
Yeah, we could select a red heart or what? Red diamond, correct? That's a red 6. 2 out of 52. And 2 out of 52 reduces down by 2, down to what?
1/26.
1/26. 1/26. Okay. So 1/26. All right. All right. What's the probability of selecting a spade? Selecting a spade. Well, how many spades are there? There's 13, correct? Ace through king. So it'd be 1350/52, which reduces down to what? If you reduce down by 13, take this down to 1/4. 25% chance, correct? Of selecting a spade. All right. So working with a standard deck of cards a little bit here gives us a little idea as to how to deal with some probabilities surrounding that. Okay. Let me bring this back up here. All right. Okay, let's see a red card in a 7. All right, for classwork number 2, I want you to answer 18A through E. So we'll call this classwork number 2. Go ahead and do those problems there. I'll leave this diagram up here so you can see. All right, classwork number 2, 18A through E. We're assuming we're drawing one card from a randomized or well-shuffled deck. All right, let's take a look here. Number 18A. What's the probability of selecting from a well shuffled deck a 6 and a spade? Well, the word "and," ladies and gentlemen, is called a conjunction. It suggests what is a conjunction is like the intersection between sets, or is a disjunction. So "and" requires that both of these statements be true simultaneously, or just requires that at least one of the statements be true. So the probability of selecting a 6 and a spade is demanding that we select one card, and that can only occur one way if you select the 6 of spades. The 6 of spades is the only way you can select a card that they got a number 6 on it and is also a spade out of 52 cards. Okay, so the probability of selecting a 6 and a spade is 1 over 52. Okay, 1 over 52. Probability of selecting a black king, that can only occur if you select a king of spades or a king of what, clubs? So that would be 2 over what, 52? Or that reduces down to 1 over 26. All right, what's the probability of selecting a red card and a 7? It has to be a red card, and it also has to have 7 stamped on it. Well, that would either be a 7 of hearts or the what? The 7 of diamonds. So that's going to be 2 over 52, which is going to be 1 over 26. All right. Whoops. 1 over 26. Son of a gun. Probability of selecting a diamond or a heart. Now, diamond or a heart means that we could select a diamond. That makes all these available. Or we could select a heart, or joins these two together. So that means there's going to be 13 ways to select a heart, added 13 ways of selecting a diamond. That's going to be 13 plus 13, or 26 ways for this to occur. 26 over 52, or 1/2. That'd be equal to 1/2. Makes sense, because that's half the deck of cards, correct? What's the probability of selecting a black card? Well, a black card can be selected also, what? 26 ways, correct? Out of 52. So this is also going to be 1/2 too for this one. Okay. All right, makes sense? Basic probabilities here. Okay, let's see what else we got here. Go down to one like 24. Rural speed limits. Rural speed limits for all 50 states are indicated below. So what do these numbers suggest here? These numbers are states that have these rural speed limits. 12 of our states, of our 50 states, have a rural speed limit of 55 miles per hour. 4 states have a rural speed limit of 60 miles per hour. 3 states have a rural speed limit of 75 miles per hour, et cetera, et cetera. So these numbers represent the number of states that fall into each of these categories here. Find the probability that a speed limit is 60 or 70 miles per hour. Well, how many ways can this event occur? 60 or 70 miles per hour? Well, that can occur 4 plus what? 12 ways, which is, they say, 16 ways. So 16 of the 50 states have rural speed limits of 60 or 70 miles per hour. So your probability of selecting a state randomly, assuming these all states are randomized, and a state having a speed limit of 60 or 70 miles per hour is to say 16 over 50. Which reduces down by 2 down to 8/25. What's the probability of randomly selecting a state and that state having greater than a 65 mile per hour rural speed limit? Greater than 65%? Well, greater than 65 miles per hour, excuse me, would be 70 miles per hour or 75 miles per hour. That constitutes 7 plus 3, 12 plus 3 or 15 states. So that'd be 15 over 50. And by 5, that reduces down to 3/10. Okay, 30% chance. What's the probability of randomly selecting one of these states and having that state have a 70 mile per hour or less rural speed limit? In other words, we want the probability that our speed S is going to be less than or equal to 70 miles per hour. Well, ladies and gentlemen, do you agree by our complementary probability rule? This would be saying 1 minus the probability of the complementary event. And what event is complementary to saying that the speed limit is less than or equal to 70? What's the complementary event? If the speed is not less than or equal to 70, it must be greater than 70 miles per hour. So this is the quicker way to evaluate this probability using your complementary probability rule. So this is going to be 1 minus what's the probability of a state having a higher than 70 mile per hour rural speed limit? That would be 3 out of 50 states. So 1 minus 3/50 is going to be 50/50 minus 3/50, which is 47/50. That's what this probability is going to be. So that's the probability of choosing a state that has a rural speed limit of 70 miles per hour or less. 47/50. Any questions about that problem there? Okay. All right. All right, let's see here. All right, let's go down to problem number 32. I one like this. Living arrangements for children. Here are living arrangements for arrangements of children under 18 years old living in the United States. States in a recent number. Numbers are in thousands. The number of children that are living with both parents is that number. Mother only, that number. Father only, that number. Neither parent, that number. Choose one child at random. Suppose we randomly choose a child. So each child has a random or an equal likelihood chance of being selected on any given trial. What is the probability that the child lives with both parents? With the mother present. Both parents. Okay. Well, I got a question for you, ladies. How are we going to compute this probability? You think this is equal likelihood here? It sure don't look like it. Those numbers don't look like they're equal in value. It's not equal likelihood. No, this is going to have to be relative frequency way of computing the probability, or we say the empirical rule way. So what are we going to have to do with all these numbers? First, we're going to have to add them all up, correct? We got to sum all these numbers up to see how many children were surveyed here. So we must add them all up. So what's the sum of all these numbers? We got to add them up. I get 74,719.
That's what I got.
Now we can answer this question. It says, if we randomly select a child, what is the probability the child lives with both parents? Well, how many live with both parents? Well, 51,823. We're going to divide that by the total number of children that were surveyed. 74,719. And you have your answer. Let's just convert this into a decimal. That'll be the probability of the first thing here. So we're going to take 51,823 and divide that by 74,000 1,719. And I'm getting about what? About 69% chance. And if I randomly select a child, that child will be with both parents. About 69% chance. Right? With the mother present, what's the probability of randomly selecting a child and the child living with the mother present? Well, how many of the children surveyed, of the 74,719 children, how many had living arrangements with the mother present? You agree that would involve with both parents, mother would be present, and also, ladies and gentlemen, with the mother only. You'd have to add both these numbers together. You're gonna have to add 51,823. You're gonna have to add that to 17,283. And then you have to divide all that by what? 74,719. That's going to be your answer. All right, so we got to do all this. 3 plus 17,283, divide that by the grand total. And I'm getting about 92% chance, 0.92. I'm going to round it off to the hundredths place. So 0.92. There you go. Hey, do you think odds are related to probabilities, ladies and gentlemen? You know, you probably always hear on the news, you know, the odds of winning a particular lottery game or lotto game, or the odds of a sports team winning, blah, blah, blah. Correct? Yes, odds are related to probabilities. And there is a rule, mathematical relationship or rule, that relates probabilities to odds. So we would say this, the let me show you what the rule is here. So odds in favor of a particular event. So the odds in favor of event E occurring is going to be equal to the probability of event E occurring divided by 1 minus the probability of event E occurring. In other words, ladies and gentlemen, the odds in favor of event E occurring is going to be equal to the probability that event E occurs divided by, what's another name for this to say 1 minus the probability of event E occurring? It's another name for this. It's called the complementary probability rule. Do you agree? This is saying the probability of event E what does not occur. Does that make sense? For instance, if we have a die, what are the odds of rolling a 6 on a die? Well, what's the probability of rolling a 6 on a die, assuming it's a fair die? So this is going to be the probability of rolling a 6 divided by 1 minus the probability of rolling a 6. Well, the probability, ladies and gentlemen, of rolling a 6 on a fair die is going to be 1/6 divided by 1 minus 1/6, which is to say 1/6 divided by 1 minus 1/6 is 6/6 minus 1/6, which is 5/6. And 1/6 divided by 5/6 is going to be 1/5. Okay. Or we see more commonly the odds of rolling a 6 are going to be 1 to 5 odds. Normally we would express odds this way. Okay. The odds of rolling a 6 would be 1 to 5. So lay down, what would be the odds of not rolling a 6? What do you think? Well, that's going to be the probability that we do not roll a 6 divided by 1 minus the probability we do not roll a 6. The probability of not rolling a 6 is going to be what? That we roll a 1, 2, 3, 4, or 5. That's going to be 5, 6. Divided by 1 minus 5, 6. So this is going to be 5, 6 divided by 1 minus 5, 6 is 6, 6 minus 5, 6, which is 1, 6. This is going to be 5 to 1 odds. Make sense? Sounds about right, right? That's the probability of not rolling a 6, 5 to 1 odds. So it depends whether, you know, you're talking about the odds in favor or the odds against, okay, as to how you represent your odds here. All righty. Okay. So the odds in favor of event E would be this. And so what would be the odds against event E? Well, that's going to be the probability of the complementary event occurring, or the probability of not E occurring, divided by 1 minus the probability of not E occurring. Okay, so that you can see there is an innate relationship between odds versus probabilities. All righty. All right, let's go down to number 47 here. We're running low on time here. 47. This is all expressed in problem 47, ladies and gentlemen, odds here. All right, I want you to do for the last classwork here. Here it is. I want you to do 47B right here. What are the odds of rolling a die and getting an even number? In other words, what's the odds in favor of rolling an even number? The odds in favor of rolling an even number on a die. Go ahead and compute the odds. The odds of rolling an even number on a die. We'll call it the last class. All right, so the odds of rolling an even number, according to our odds formula, is equal to the probability that we roll an even number divided by 1 minus the probability that we roll an even number. What's the probability of rolling an even number? That's the probability of rolling a 1. Wrong. That's the probability of rolling a what? 2 or a 4 or a 6. Divided by 6 possible outcomes. Do you agree? And we're assuming an equal likelihood model, assuming our die is fair. Well, how many ways can you roll a 2, a 4, or a 6? That's 3 ways. So the probability of rolling an even number is going to be 3 6. And then we're going to have to divide that by 1 minus 3 6 to compute the odds in favor of rolling an even number. So this is going to be 3 6 divided by 1 minus 3 6 is 3 6. So the answer is, ladies and gentlemen, you got 1-to-1 odds. 1-to-1 odds of rolling an even number. So what would be the probability, or excuse me, the odds of rolling an odd number? What do you think?
Also 1-to-1.
1-to-1, you got it. All right, that's all the time I got, ladies and gentlemen. I've exhausted and wore out my welcome. I'll open up this homework on 4-1. And we don't have any assessment this week. We will next week, but I'll stay on the line if you have any questions or comments. By all means, let me know. Other than that, have a great day.
Have a good day.
Thank you. Have a good day.